Assalamualaikum warahmatullahi wabarakatuh. Today, we would like to present our lab report entitled Power Factor Corrections. We are from group 1.4, section 1. So, my name is Naim RIZUAN bin ZAID and my lab member is SCOVIEN OLLE Lawrence and also Muhammad Nurazim bin HAYADIN. So, for the first one is what is power factor? So, power factor is a cosine of the angle between voltage V and current I. For example, cos theta. As you can see the formula, power factor equal to cos theta, which is active power over apparent power. P over S for the unit is watt over VA. So, low power factor is caused by inductive loads like ballast, induction furnace, induction motors, and etc. So next, low power factor has many disadvantages such as large rating of equipment, greater conductor size, large copper losses, poor voltage regulation, and reduced handling capacity of the system. In this project, we can improve the power factor by adding shunt capacitor. Okay, well, as you can see, this is a power triangle. So for the hypotenuse is the apparent power, unit is kVA. And for the adjacent is real power P kilowatts, and the opposite one is reactive power, or as we can see as Q is equal to sin theta. So next, this is a behavior of power factor vs load type. So for the circuit, we put the inductive and also the resistance. So the value for Q will be positive. Meanwhile, we put the capacitive load. The value of Q will be negative. Okay. The variance of power factor vs reactive power. As you can see, the angle will be less than 90 degree. Between 0 and 90 degree for the reactive power and also the apparent power. Okay. Next, what will you do for this activity? Okay, the first one is understanding the power factor correction method. Next, reduce power loss and improve efficiency, as well as the current carrying capacity of lines and voltage regulation. The power factor must be improved. Furthermore, end user can reduce the additional billing as it's an improvement of 90%. Power utilities required is to be close to unity, but to 90 to 95% is acceptable. Next, since power correction takes place by adding shunt capacitor, therefore its QC cancel out the plus QL to maintain angle difference as nearest to 0, resulting power towards unity 1 because cos theta equal to 1. Calculate the value of QV. Compensating Q component to eliminate QL with L component to achieve of power factor of 0.95. Calculate capacitive reactance XC and QC for delta as well as the combination to observe whether this calculated value can be applied or not to achieve 0.95 power factor. Last one, insert the value has been calculated in the table. Okay, next for the experiment power factor correction.
I will continue for the experiment power factor correction. My name is Muhammad Nurazim bin HAYADIN. Okay, the connection of the system for the laboratory session is this one is the supply unit, which which is the circuit breaker for the digital measurement unit and our analog measurement unit. So what we need to do first is we need to connect our main supply to our circuit breaker phase by phase. So we start with red phase and blue phase, and after that from our circuit breaker we can head to our load, red phase, yellow phase, and blue phase. And after that, we can connect it to our analog measurement unit. So red phase and yellow phase. This will measure the voltage line to line from red phase to yellow phase. And next, we need to measure our light line voltage between yellow phase and blue phase using our digital measurement unit. And then we need to connect our circuit transformer to our measurement unit to measure the current in series. Naim, stay at up. Yes. After that, the connection to the system, we can proceed to connect our resistive and inductive load. Okay, for the next slide. This one is the resistive and inductive load. For the left side is the resistive load, and for the right side is the inductive load. So the connection is from our system is the red, yellow, blue, and neutral. So we can proceed to connect red phase for the resistive load and go to the inductive load for the yellow phase, and then for the blue phase, and then finally for the neutral. So after we done our connection here, we can measure our power factor before we can get a perfect power factor correction. When we need to add our capacitive load, so in the next slide, we'll be connecting our capacitor load. So this is our capacitive load. We'll proceed for the connection, and red, yellow, blue initial will become formal supply for the connection. Red and then yellow and then blue, and finally for the neutral. And then for the connection, we add our capacitive load when we want to do our for the power factor correction, and then we can get the perfect power factor correction. That's all from me.
Okay, hello, my name is SCOVIEN. So I will present about the expectation on power factor. So as we can see from table 2.1, from the top left, that is the step for switch inductor and resistor. Next to it is I line, and next to I line is power factor. Both of the value is given, and we also know the value for our voltage source, which is 215. So from that, we can simply calculate for our power input. We can see that when I line increase, the power factor will decrease. So the desired power factor, or the power factor that we want for our improvement, is 0.95 for all. So in order to do that, we need to add certain amount of capacitance, right? So let's look at step 1 for switching 1 to 1. Our initial power factor is 0.85, and our desired power factor is 0.95. So we improve from 0.85 to 0.95 by adding 622.4 watt. And then we look at another case, step, switching 5 to 1 for the third resistor. Initial power factor is 0.56, and the desired power factor is 0.95. So when we improve from 0.56 to 0.95, we add 2,733 watt. We can observe that the lower the power factor, the higher the amount of capacitance that need to be added. So as a result, the expected power factor, of course, should be 0.954 above, because the desired power factor is 0.95, which is objective. So the expected power factor should be same or more, and it cannot be less. Okay, next. Why power factor correction is important? So the first one is saving on electricity bill. Power factor correction eliminates penalties on reactive energy, decrease demand on KVA, and reduce power losses generated in the transformer and conductors of the installation. Second is increase available power. Fitting PFC equipment on low voltage side increase the power available at the secondary of MV LV transformer. A high power factor optimize an electrical installation by allowing better use of the components. The third one is reduce installation size. Installing PFC equipment allows a conductor cross-section to be reduced, as less current is absorbed by the compensated installation for the same active power. And the last one is reduce voltage drop. Installing capacitor allows voltage drop to be reduced upstream of the point where the PFC device is connected, therefore preventing overloading of the network and reducing harmonics. Okay, that's all from us. Thank you.